Now let me introduce our next speaker. I'm delighted to introduce Professor Tomaso Poggio of the Department of Brain and Cognitive Sciences at MIT. He's the director of the NSF Center for Brains, Minds, and Machines at MIT. He is one of the most cited and one of the most foundational thinkers and researchers working at the intersection of cognitive science and computer science. His list, this is one of the bios where you hesitate to omit something because it has a lot of wonderful accolades on it, but I checked with him earlier and I'll just highlight a few. He received the 2003 Gabor Award, the Okawa Prize in 2009, the 2014 Schwartz Prize for Theoretical and Computational Neuroscience, and Lifetime Achievement Awards from the IEEE. He's also, over the course of his career, spent a lot of energy in making sure that the industry benefits from thinking in academia by participating in starting companies, advising companies, being on the board of companies. And as might befit somebody who is going to tell us about the science and engineering of intelligence, I think, Professor Poggio, you've spent a lot of energy shaping the intelligence of your students, your PhD students and postdocs that have gone on to found companies like DeepMind. So please welcome me in, please join me in welcoming Professor Poggio.
Thank you for everybody to come here and to Fujitsu to invite me, in particular Hirokazu and I, Seishi Okamoto, and our CEO Shigeru Sasaki. I have to announce a wonderful partnership between our center, the Center for Brains, Minds, and Machines, and Fujitsu Labs. There have been news just in the last few days. This will be a collaboration from which I expect a lot of good results. And this will be on the engineering of intelligence, but also on the science of intelligence. We had in my group for the last more than a year a wonderful research scientist from Fujitsu. This is Tomotake Sasaki. The arrow indicates him, and it has been a great beginning for what I think could be a very great interaction. So let me explain when I said engineering of intelligence, what I mean. And so let me tell you a little bit about the center I'm directing. This is the Center for Brains, Minds, and Machines. Its focus is the science and the engineering of intelligence. We aim to make progress on the problem of intelligence, which means understanding how the brain works, how it creates the mind, and how can we replicate all of that in machines. Now, personally, I think that the problem of intelligence is not only one of the great problems in science, like the problem of the origin of the universe, or the problem of the origin of life, or the problem of the structure of space and time. It is the greatest of all. And the reason is, we can argue about it, but the reason is that if we make progress in the problem of intelligence, then we can solve much more easily all other great problems. Progress on the problem of intelligence means that we can make ourselves smarter, and we can build machines that help us think better, and that's actually going on. The center is one of about 12 nationwide centers in the US, funded by NSF at the tune of $50 million every 10 years. It's a multi-institution center. We are beginning the phase 2 after the first 5 years, the next 5 years. And we are a combination of computer scientists, so engineers, and neuroscientists and cognitive scientists, kind of the three disciplines you can identify are especially important for studying, making progress on the problem of intelligence. There are about 20 faculty or so, 200 researchers, including students, graduate students, and postdocs. We have several academic partners. The main two are MIT and Harvard. And again, in the faculty there, you can see people that are in computer science and people who are in neuroscience, cognitive science. We have corporate partners, of which Fujitsu is now one. Welcome. And they are the usual suspects in working on the problem of intelligence. Some of our early partners were small 5 years ago, like DeepMind and Mobileye, are now part of bigger companies like Google and Intel. We had a pretty good external advisory board comprising a number of philanthropic and business people and friends of mine who have contributed quite significantly to progress in AI in recent years. For instance, Demis Hassabis is the founder and CEO of DeepMind. Fei-Fei Li is at Stanford and Google. Mark Raibert started Boston Dynamics, is one of the most advanced robotics companies. And Amnon Shashua started Mobileye, autonomous driving. And David Siegel started a very quantitative and very successful hedge fund called 2 Sigma. Among our activities, one of the most successful ones has to do with education and actually preparing a next generation of researchers that are fluent in both mathematics, computer science, and neuroscience. We have a 3 weeks school for mostly graduate students and postdoc at the Cape Cod, which is a popular vacation place for New England. And the course involves projects that the students have to do during 3 weeks under the advice of TAs, technical assistants who have had experience with the school already. And so the students have access to a range of expertise from neuroscience to computer science. It's really kind of trying to create a new community of scientists. It's interesting how summer school have been playing a big role in science. For instance, molecular biology was really created by a summer school at Cold Spring Harbor that Max Delbruck started in the beginning of the 50s. We are now at MIT, the success of CBMM so far has convinced our administration to start a larger effort within MIT called the Quest for Intelligence. It was launched in February, and it's essentially extending what CBMM is to other problems of intelligence. Intelligence is just not one problem, is many. Like biology is not one problem, is many problems. And you can think of the MIT Quest as an effort which consists of a bridge and a core. And the bridge has to do with giving application, helping the all of the institute, so not only computer science, but for instance the biology department, with software tools and engineering expertise in AI, right now, especially in deep learning. The core is where research takes place, and there you can distinguish 2 areas. One which is what I call the natural science of intelligence, basically neuroscience and cognitive science. This will be human intelligence. And the other, which is engineering of intelligence, so computer science, machine learning, and so on. And what I personally find most interesting is the intersection of the two, which is what, for instance, our school is about, creating researchers that are both engineers and scientists. Let me give you a little bit of history. At MIT, what we're doing is not new. It's really the logical following of what happened in what I call the golden era, 50 or 60 years ago, when at the same time at MIT, Marvin Minsky started artificial intelligence together with John McCarthy of Stanford. They invented the name. Noam Chomsky started the quantitative formal study of linguistics, so cognitive science, and Norbert Wiener and Claude Shannon has really established the foundations of information theory and control theory. And more recently, we had these efforts, an MIT Intelligence Initiative in which I was involved, and then the Brains, Minds, and Machines Center, and then now the MIT Quest. Just to tell you, I use this term science, not to say that engineering is less than science, not at all. I'm using the word science in the same way that Francis Crick used to do it. Francis was the discoverer of the structure of DNA with Jim Watson, who was an old friend of mine. And he was very insisting that science is natural science, is studying things that exist in nature, like physics, chemistry, biology. Mathematics is not science. Is studying human artifacts. So that's just a convenient distinction. And so we want to really focus on both the natural science and the engineering of intelligence. Now, there are many reasons why it's important to focus on the science of intelligence and not only on the engineering of intelligence. Companies like Google tend to focus on the engineering and forget the science. But there are good arguments to say that the natural science, knowing how the brain works, gives good inspiration also for the engineering. This is a paper by Demis Hassabis, who was a postdoc of mine and is the founder of DeepMind, in which they argue that if we want to really to solve artificial intelligence, to have more breakthroughs, we need to pay attention to neuroscience. And this is from a lab, a group, DeepMind, which is arguably the most advanced in the world in AI. Another point about this is, two recent success stories in AI. For me, they are the two prototypical ones, partly because they were both my postdocs. One is AlphaGo, so beating humans at games like Go and chess and so on. And the other one is autonomous driving. So on the left is Demis Hassabis, on the right is Amnon Shashua. This was the scenes. I was at the last Go game in Seoul when AlphaGo won against Lee Sedol, the unofficial world champion of Go. Go is very popular in Korea, so there was a lot of media attention. And this is Amnon Oh, sorry. Let me see if I can go start. Okay. So this already 4 years ago. And um, just showing the vision system that Mobileye developed to autonomously drive a car. And that system works very well. You can, actually it's an interesting comparison. Just see. Let me try to go back, sorry. Okay. So back in 1995, my lab had a joint project with the research group at Daimler, so Mercedes, and we developed one of the very first applications in machine vision of machine learning. So we trained a system to detect pedestrians with a few thousand images of people in Boston, and then ran the software. This was in the computer in the trunk of a Mercedes, driving in the streets of Ulm. Ulm is where the research labs of Daimler are. It's also the place where Einstein was born. And if you can look here, we had some mistakes in this detection, right? There were some false alarms for either detecting the traffic light as a pedestrian. In fact, we were very happy about the results at the time, but we had one error every 3 frames, so 10 errors per second. So the system was scientifically interesting, but in practice unusable. Now, on the same problem, Mobileye today has an error rate of about 1 error every 40,000 kilometers of driving or so. Back of the envelope calculations tell you that there was a 1 million times improvement in accuracy, which is doubling accuracy every year for 20 years. So that's my Moore-like law for machine learning. That's why machine learning has become practically applicable in many different things, from Alexa to Siri to autonomous driving. So, and the interesting point is that in both AlphaGo and the vision system of Mobileye, there are 2 core algorithms. One is deep learning, the other one is reinforcement learning. If you look at reinforcement learning, this comes, it's a long history, 100 years old, but it starts with Pavlov and studies of the behavior of animals. And then Donald Hebb, and then one first implementation of a reinforcement learning algorithm by Marvin Minsky, and that was on the right, was 1 neuron implemented with vacuum tubes in the machine that he built, simulating the choices that a mouse can make in a maze, using reinforcement learning to solve the maze. And deep learning, it really started with a suggestion by David Hubel and Thorsten Wiesel at Harvard, recording from visual system of the monkey and describing an architecture that was made of layer of cells, from simple to complex cells to hyper-complex cells, each one with a local connection from the layer below. And if you look at the architecture today in the most advanced deep networks like ResNet on the extreme right, they have exactly the same type of architecture. A different way to train, but the same type of architecture. And so both reinforcement learning and deep learning come originally from neuroscience. And if you ask me, where the next breakthrough is going to be in AI, in machine learning, I would say that, of course, I don't know, but that I think is likely also to come from neuroscience. By the way, one of the first, actually the first quantitative model following up on this qualitative proposal of Huber and Wiesel was by Fukushima in Japan. And the architecture he had is very similar to this layered architecture with local connectivity that has been then repeated in a lot of other models, including the most recent deep learning algorithms. So let me tell you a little bit about what we're doing right now at CBMM, or planning to do for the next 5 years. The problem we are going to focus in the next 5 years is the problem of visual intelligence. How is it that when I'm in a room like now, I look and I have a pretty good understanding almost immediately of what's going on? You know, where people are, what they're doing. If I need to walk from here to there, I know almost immediately where the obstacles are. I can plan qualitatively my trajectory. And so this understanding of the visual world is something very powerful. It's almost similar to being conscious when I open the eyes. That's why I call visual intelligence video ergo sum. It's cogito ergo sum, Cartesian, but instead of cogito, the experience of vision is very strong. There is an experiment that people have done also at Google in which you, the subject, sit in a chair, you have a robot nearby, you're looking through virtual reality glasses, and you're seeing what the cameras on the robot's eye are seeing. And you move the head, and the head of the robots move. Okay, the sensation reported by the subject is that they feel they are where the robot is, not where they are physically are, even if when they look at themselves through the eyes of the robot. It's very, very strong. You cannot escape it. It makes sense because your eyes are effectively where the robot is. But just to say that this kind of sensorial experience is very closely related to what we call self-awareness, you know, awareness of ourselves in the world. So the question we ask is, which kind of computation are going on in our brain to create this full understanding of the scene, the environment around us? And we have identified 4 different set of areas in the brain that are involved in early processing of vision, the visual stream, in kind of a brain OS, the working memory and decision controlling eye movements and so on, and other areas. And so you are planning to try to understand this computational organization, meaning doing experiments with physiology, both in monkeys and humans, using fMRI, MEG, other non-invasive techniques, and implementing what we found on computers. One other aspect of all of this is just to give you some of the puzzles that we are trying to answer, is that at every glance that we have in the environment, we only see with high resolution a very small part of the visual field. The kind of resolution that you need when you go to the ophthalmologist to check your sight, and you have to read the small letters at the bottom, it's very restricted. It's only probably 1 degree of visual angle where we have this high resolution. It's the size of my thumb at this distance from my eyes. So somehow the brain assembles high resolution fragments through different fixation in the environment and creates a computational illusion that we see everything at high resolution and we can act on it. So these are examples of additional moonshot projects of the same size as the CBMM, visual intelligence, that have to do with other questions about intelligence, how it develops, what is the underlying hardware, what it means to plan and imagine, and other issues about emotional intelligence. And finally, how did evolution discover language and what are the circuits underlying it? That's a uniquely human capability, language, that no animal shares with us. Did evolution discover some specific cortical circuit that you cannot find in monkeys, for instance? And this leads me to the question about, which is the main topic of today's symposium, is about ethics. And here, there is often an ethics of neuroscience, neuroscientists being ethical, but what I want to address here is the neuroscience of ethics, is which parts of the brain underlie ethical behavior. First of all, just a few general comments about AI and ethics today. I think I strongly disagree with statement like Hawkins and Elon Musk had a couple of years ago that AI is more dangerous than nuclear bombs. I think that's simply not true right now. We are a long way from that. And I think that what we should discuss today are more practical and immediate issues about AI. Part of the reason why I disagree, I think the progress of AI is going to be slower than people think. There will be a lot of interesting spin-offs and results. A lot of them is a golden age. But in terms of making machines that cannot be confused with ourselves, it will take quite some time. Demis Hassabis thinks 20 years. I think more like 100. We'll see. The pressing issues are, first of all, the usual issue that jobs are lost to technologies, to powerful technologies. This is not the first time. It happened with railways. It happened with the steam engine. This time may be faster and more pervasive than other times, and so we should be prepared to disruptions in the society and try to avoid that. There are practical issues for academia, or say DeepMind, is, if some discovery can be especially dangerous, maybe one should decide not to publish. In general, I think publication is good, and it's always better to discover if the good guys discover something dangerous rather than let the bad guys do it. So in general, I'm in favor to publish, but of course this has to be carefully decided. DeepMind, for instance, has an ethical board for dealing with this kind of potential issues coming up. But if we look at the future, I think a very interesting question is what is the origin of ethics in our brain? And can understanding of the ethical machines in our brain, can that help us build better machines? And maybe even teach us how to become better ourselves, or how to more effectively teach people about ethics and being ethical. A colleague of mine, Rebecca Sachs, has been doing fMRI studies through which you can see activity in the brain of humans. And she found that particular areas of the brain, she's not the only one with this kind of results, the particular areas of the brain are associated with specific cognitive functions. For instance, specific areas of the brain become active when you think about other people's behavior. This would correspond to what cognitive scientists call theory of mind. It essentially corresponds to putting yourself in the shoes of somebody else. And there are parts of the brain that you can actually influence. There is a technique called TMS, transcranial magnetic stimulation, in which you influence the activity of the brain locally by having pulses of magnetic field close to the surface. And you can, doing this, change the responses of people to specific ethical questions just by stimulation of the brain. This brings up a lot of interesting ethical issues, legal issues, and so on. But hopefully, understanding what's going on will help us understanding how to make, among other things, ethical machines, ethical computers. The kind of twin theme that comes with ethics of AI is that we need to understand better what AI systems do and why they do what they do, and when can they be wrong and when they should be right. It's kind of ironic that we have these days quite powerful implementation in deep learning especially, and they're used in a number of applications from autonomous driving to games, to speech recognition and so on, but we still don't know why they work the way they work. You know, there is basically heuristics, and there is very little theory. Now, it's not uncommon in science that this happens. If you think back at what happened with electricity, I know the story pretty well, was discovered by Alessandro Volta in the year 1800. It was made a count by Napoleon because of that. Until then, information traveled in the world at the speed of a horse. And then with the discovery of the electricity, essentially few years after that, there were telegraphs with information traveling at the speed of the light. It was a major, major revolution. And it was an accidental discovery. Alessandro Volta discovered the pila, the battery, because he wanted to show that an academic colleague of his, Galvani, was wrong. Typical motivation in academia. There was no theory, but this did not impede the fact that Alessandro Volta himself designed a telegraph line between Pavia and Milan. It's 30 miles. And after a few years, the whole electrochemistry was done, and there were electrical motors and generators. But it was until Maxwell, 60 years later, that there was a real theory. And that, of course, created a whole new area of science, including radio and telecommunications and so on. So I think with deep networks, we are still in the kind of this, accidental discovery phase. And the question is to develop a theory that will allow to expand these techniques and improve their efficacy. So I was planning to give you a little explanation of where we stand in terms of the theory. How many of you know deep networks? Can you raise your hand? Okay, so stay with me. A network is made of several layers. Each layer is a set of neurons. For this example, you can think of input being an image, thousands or millions of pixels, and then there are various simple transformations that go on, and think until at the end there is, for instance, a label, if that's what the neural network has been trained to do, saying which image is, which object is in the image. And in fact, deep network became very popular with this work in 6 years ago, 5 years ago, that was doing exactly this kind of classification on a set of images, 1 million of them, called the ImageNet, where you have different, about 1,000 different types of images, from cars to buses to dogs to ships and so on. And the task was to classify each image. And as I mentioned, we need to get some theory, because so far the spectacular recent success of deep learning are really empirical. This was a course last year by David Dono, who is the main, one of the top statisticians in the world. And so if we look at what's going on between the layers, what happens is pretty simple. You have units, call them neurons, and each neuron receives inputs from either the image or the layer of neurons, the layer below. These inputs are numbers, and each input line has a weight. So what the neuron does here is a sum of the weighted activities of the previous neurons. And then this sum, which again is a number, remain the same number if its value is above 0 or gets put equal to 0 if it's below 0. So just a kind of linear rectification. That's it. That's what a neural network does. And the trick is to find the values of the weights for all the layers and all the neurons. And this is done during so-called training, in which you are trying to find the weights that give you the best results on a training set, where you have images and you know the correct output. So you can imagine you can tweak, in principle, all the 1 million weights or several million weights until you find a situation in which you get, for each of the images, the correct answer. That's basically what training is about. Mathematically, you are doing something which is called gradient descent, or more precisely, stochastic gradient descent. You are changing the weights in a way to minimize the error over the training set. And amazingly, you get pretty good results doing this. You find weights where you have mostly correct responses on the training set, and then when you try new images which were not on the training set, you get pretty good results. Okay? So what are the main puzzles here? One question is, why are deep networks with many layers better, why and when are better than shallow networks with one layer? And shallow networks with one layer turn out to be essentially the classical machine learning techniques, including linear regression, that people have used until recently. So why, when one is more powerful than the other, and why? And then the other two puzzles are, one is about optimization, why it's so relatively easy to solve this optimization problem of finding the weights. It's a huge optimization problem. It's non-convex, there are millions of known the weights, million of data points, that the example, the image, how is it possible that it's so relatively easy? And the third is probably the most puzzling, is that typically in the neural networks used today have more parameters than the data used to train them. Now, this is kind of counter to everything I've been taught when I studied physics in my youth. I was told if you have a model that has 10 free parameters, better have at least, of course, at least 10 data points, but you have to have 20 and maybe 100 in order to reliably find those parameters from the data. So, very important, have less parameters than data. Deep networks today are exactly using the opposite setup. You have more parameters than data. And despite that, this is a situation in which you may imagine you can fit the data, but not do well on new data points, what is called generalization. But despite that, they do quite well. So why? And I think we have answers to all of them by now. So I think that we have a beginning of a comprehensive theory for deep networks, most of which is still unpublished. I'll tell you briefly the main answers here. The first one is about when are deep networks better than shallow networks? And it was well known since the 80s, and this was one reason why people did not focus on multi-layer and focused on single-layer networks. It was well known that if you want to approximate an arbitrary function very well with a network, you can do it arbitrarily well with a one-layer network. It's a kind of Weierstrass theorem. You can approximate with a polynomial every nonlinear function, continuous on a bounded interval. But what people did not think about is that when you do so, you have what is called the curse of dimensionality. In other words, you need a lot of parameters in doing that. And the number of parameters depend exponentially on the dimensionality of your input. In the case of the image, how many pixels you have. In fact, if you want to have an approximational accuracy of 10% and your inputs, the dimension of your vector input is, say, 8, you need 10 to the 8 parameters in general. 10 to the 8 parameters is not too much, but if your input, instead of being 8 dimensions, is 1,000 or more, like in the images case, then when you have 10 to the 1,000, that becomes a very large number. So both shallow and deep networks have this curse of dimensionality problem, but deep networks can avoid this curse of dimensionality for specific classes of functions. When the function of d variable, in this case 8, it depends on functions that are local, have a small number of variables, then it turns out that deep networks, but not shallow networks, do not have the curse of dimensionality. And so, and they become, instead of being exponential in the dimensionality, I have a fixed number, which is the locality of the constituent functions, and are otherwise linear in the dimensionality. We have checked that with various simulations, and it seems to be the reason deep networks of the convolutional type, which are the most successful, seem to be the reason this works. Of course, this brings up other questions, because this implies that the task we are doing with convolutional networks like image recognition, speech recognition, text recognition, have this compositional local structure. And there are various reasons why this is probably the case. In the case of text and speech, they are human artifacts. They are made up of parts, words made up of letters, sentences made up of words, paragraphs made up of sentences. So it's natural that there is this compositional structures. For images, it looks like it's a similar situation, but it's a bit more difficult to understand why, whether it's because the Hamiltonian of physics are local, which is what my colleague Max Tegmark in the physics department claims, or because our brain is wired up in that particular way. Anyway, let me go quickly to a couple of the other two questions about why it's optimization easy. And here I will just say that there is this wonderful property of stochastic gradient descent that it will essentially concentrate in probability. So we'll find minima that are broad. You can see here a situation in which there is two minima that you have to find during training. This is the loss function. And one minima is degenerate. The other one is not. They're both as deep, equally deep, but because of the degenerate property, the volume in parameter space of the degenerate one is much larger, and this implies that stochastic gradient descent in 2 dimensions will prefer the degenerate one to the other one, despite they are both equally deep. And in a million dimension, this one will disappear, cannot be seen. It will find only the degenerate one. And it turns out the degenerate ones are the global ones. You can prove that. So stochastic gradient descent has this magic property of finding with high probability global minima of the loss. Okay. There is this other question about third puzzle, which is why the deep networks manage to predict well despite being over-parameterized. And we have a pretty good understanding of this, which is for technical people around you, it's essentially saying that the situation is similar to the pseudo-inverse, to the situation in which you have a system of linear equations and you have more unknowns than equations. So there is an infinite number of solutions. But the pseudo-inverse solution of that is that you, among all those infinite number of solutions, you pick up the one with minimum L2 norm. Same thing happens, very similar things happens with deep networks. So they will find the solution which has the minimum norm and is the most predictive one. It's a bit complicated to explain it, especially in 2 minutes, but I'll show you consequence of this, in which if you plot the error in training and the error in testing, you find completely, no particular relation. They are different from each other. You cannot, from the performance in training, you cannot predict how well your system is going to do in testing. And this was one of the problems. There is a well-known paper saying that we have to develop a new machine learning theory to understand this phenomenon. But by making a simple transformations on the weights of the network that comes out from this theory, I mean, it's essentially normalizing in a certain way the weights of the network, we can be in a situation which exactly the same data are now seen. The train loss on the training set is a very good predictor of the test loss for different types of networks. So we can predict which ones are going to do well and the ones who are not going to do well on new data. Okay, so there are, as I mentioned just in the last minute, I'll tell you about future breakthroughs. As I said, I don't know what they would be, but here are just some speculation about things that may happen in machine learning and deep networks, especially new learning algorithms instead of stochastic gradient descent, more biologically plausible. Stochastic gradient descent is not. But in general, I think, let me finish with a couple of kind of musings. We are in a time in which is now has replaced programmers with people who label data. You know, they're cheaper. But the ideal is, of course, to do like children do. Children learn to recognize an object or objects without the need of 1 million labeled examples. When you show it, you don't need to show 1 million images of cars to a 2-year-old in order for this to understand, to recognize cars. So I think from the point of view of AI, we are now in the phase of big data. I mean, n going to infinity as big as it is. These are labeled data. But the ideal is to go to n going to 1, like for children. And big data, of course, in some instances, allows us to do things better than humans. Think about Google search. But if we want for many other things, and for making machines that are intelligent as we are, we need to go to this next step. Thank you.
Professor, thanks for your insights. The question I have is regarding the ethics. You did mention regarding putting a magnetic proximity to the brain. Are we trying to change the behavior, or are we trying to actually accentuate the hidden thinking of human brain to actually express itself in an ethical manner?
It's an open question, what we are going to do. I think, in general, in artificial intelligence, one of the goals is, to build a machine. I'm speaking about academic goals, which passes the Turing test, which can be confused by another person for a person, right? It behaves like a human being. That would be kind of ultimate goal of artificial intelligence. Now, practically, I think that we can learn a lot about our own brain and ourselves in doing this. And I'm particularly interested in that part of the story, in how to how to understand what's going on in our brain and how to possibly improve it, including making better people. You know, making better people in the same sense in which we are trying to teach people to be good in school. I think, of course, all of these things come with ethical questions, which are a mix of AI and possibly biology. But you know, I think we cannot escape from this ethical question because we are afraid of the power of the technology. Technology can be very good for everybody, and it will poses us difficult questions, but we can answer them, and the advantages will be much greater than the risks.
You spoke about the school for bots, as you described it. There was a previous generation of efforts related to labeling and learning. I'm thinking of what happened at MCC with Doug Lenart's group and some of those. Is there anything to be learned or rejected from those earlier approaches?
Can you tell something more about those earlier approaches? I'm not sure I...
Sure. This was the system that was called CYC, C-Y-C.
Uh-huh.
And some of the work that they were doing in frame-based representation reasoning in terms of labeling, and then using heuristic approaches to do the same kind of unsupervised learning. It was a different set of techniques, different approaches, but you know, a considerable body of work.
Yeah. Well, I don't know the details of this, but in general, I think that there seems to be a trend presently especially in the deep learning community, towards becoming much more acceptable of all the work in AI, especially at the level of you know, logic and traditional heuristic techniques. So we'll see what happens, but in a sense, I think that deep learning has been, of course, very successful, is addressing especially the kind of sensory intelligence, like vision, audio, and so on. This is where the main successes have been. It's not directly addressing issues of logic and decision, and so, which were the main focus of the previous effort. So it makes a lot of sense to try to combine the two and go from there.